I'm going to review quickly what we've done last time. Um, so also maybe a few things. On Friday, what I plan to do is go back to the lab and do another little demonstration on one of the equipment that we're going to talk about today. So remember, for the vibration, I had you split into groups, so we'll do the same thing, but we'll flip the order. So if you were lucky, or I would say not lucky, to get the first flight, you'll get the second one. And so I'll send a little announcement on this later today. So last time what we did, we reviewed shocks. Because it was a little while since we talked about these. So we covered some of these equations, okay, that link the maximum deflection. Thank you, Laura. Maximum deflection and maximum acceleration. We revised that equation, made sense physically of what's happening. Actually, we're going to talk about these relations again soon. We talked about the working length of a cushion, and we also did an example that was going around to calculate the modulus of elasticity of a needed material in the case of a 1.5 meter drop with a maximum acceleration of 50 G. Oops. So that's the example that is passing around. So we also covered, again, so those of you who just arrived, there's a handout at the entrance over there. We covered some of the facts about shocks. We also mentioned that some of these are true, some of them are actually based on statistical tests that were done. Some are also disputed depending on how the package are handled. So guys, a lot of you arrived late. Please try to make sure you arrive on time. Okay, some it's systematic, some it's really rare. So please try to come on time. I would really appreciate that. Okay, I think that's... Oh, we also discussed a little bit about shock amplification. So let me just review that one more time so we understand what's going on. This is very similar to the magnification factor. That's why I did not go into great details on it. It relates on the acceleration that is felt by a critical component to the acceleration that is associated with an impact. So that component, based on its own natural frequency, will feel a different acceleration based on the duration of the impact associated with the main impact, basically the shock that is applied, or I would say felt by the product itself. So we don't have an equation to calculate the amplification factor. What we do have is that table that links the natural frequency to the impact frequency or input frequency. And that input frequency is related to the duration of the shock. So this is, I think, pretty well explained here. So the duration is half the period. Okay, if you were to continue that half sign, impact throughout a longer period. So if you do this, you identify that shock duration is half the period, and identifying that the period is 1 over the frequency, you end up with that equation to calculate the input frequency for that equation. So once you know the input frequency, you know the natural frequency of your component, you can go in that table and find the amplification factor and multiply whatever input acceleration associated with the shock to the product is measured, multiply this by the amplification factor to get the acceleration that will be felt by the product, the critical component. Next step, okay, we're going to the series of slides I passed on Monday. That thing can open. Okay. So we refer to that as DBC, but we're going to call the acronym stands for Damage Boundary Curves. Damage Boundary Curves is DBC. So what are damage boundary curves and what are they doing? So this is a little bit of an eye chart, but in a nutshell, the damage boundary curve is a procedure or a tool that is used to quantify the fragility of a product. Okay, I'm not talking about a packaged product. I'm talking about a product itself. So to be able to design a package to protect the product during shipment and distribution, okay, you need to know its fragility. Okay, so obviously we need to know some of its characteristics. We already talked about this previously. That's why we talked about vibration and we looked about finding natural frequencies of a product that can cause problem. Okay, now we're talking about shocks, and in this case we have to look at what kind of impact damage the product. Okay, so this is based on the ASTM standard. Okay, we're going to talk more about ASTM standard later, but that standard is D3332. Okay, and it's titled Mechanical Shock Fragility of Products using Shock Machines. So the nice thing for you guys being students at the university, and it's used not to be the case, and now all ASTM standards are available for you. You can download as much as you want. Okay, it's pretty convenient compared to when you had to go to the library and make copies of all these standards, which was a little bit painstaking and expensive. Back then it was 13 cents a copy. I don't know how much they charge you now. But
10 cents a copy.
10 cents? It went down? My goodness. Anyways. So the last time I went there, I had so many copies that I asked the librarian, and he brought me to the back door, and I made a copy there, and the people were looking at me, what are you doing? I said, I had the permission to make copies. But because I cannot take out those ASTM books, it didn't let me take them out. So anyways, now I don't have to do that anymore. So what do you need for this? You need a shock machine. That is why on Friday I want to show you the shock machine, how it works. Okay, it's really loud. Okay, so what it is, it's a big table. Okay, solid table, and in our case, I think it's aluminum. You may have some steel parts on it, but that you can raise, and it drops. Okay, so one thing that is pretty interesting about this is that the shock machine must be equipped with a braking system. Okay, so that means that, let's see. So once the table drops, okay, you're going to have a rebound velocity. So it's going to go back up, and you're going to have a braking system that catch the table, okay? Because you want a unique impact each time, okay? You don't want a table to do boom, 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 okay? Have many impacts. So that is important. So to create the damage boundary curve, as we will see later, we need both half-sine and trapezoidal shock pulses to be created. Okay, so the half-sine impact are obtained using polymer programmers. So what the heck does that mean? We're going to show you a little bit later. They have elastic properties, and they will create those shape that are going to be looking at half-sine impact. And trapezoidal impacts are going to use pneumatic cylinders. So just to make sure as well, okay, that you understand this, the half-sine impact in a perfect world, okay, they look something like this, right? So if you look, when we're going to do, hopefully everything is going to be working good in the lab, your impact might be something like this, okay? And the same thing for a trapezoidal impact. We kind of represent them like this. In real, when you do a real test, you may have something like this, okay? Your accelerometer output may look something like this. It's not perfect, okay? But that's what we're going to be getting. So what are we talking about and what does this thing looks like? So this is a shock machine, okay? And in here we identify different components. So at the top here, that big piece, chunk of metal here is the table, okay? And you have a bunch of location where you can attach, you can bolt down product on the table as well, because the thing you don't want is you don't want the product to fall off after the impact. So typically you'll have to fasten the product on the shock machine on the table. So the whole thing actually has like pneumatic system, so it has air cushion, otherwise it will just be such a big shock to the building that people are not like that pretty much. And you have those two different components. So as you see, you have these black cylinders here all around that piston here, or plunger I should say, are the polymer programmers. So there's two ways to create those impacts. And you see, you can understand that as that table falls, those plungers go in those holes, right? Okay? So if you want to do half-sign impulse, you need that these holes have to have no pressure in it at all. So you have, because there are pistons in these guys. I'm going to talk about it a bit later. So if there's no air in here, those pistons are down, okay? And the impact occurs on those polymer. The plunger will go in the hole, and you see those circles all around these felt pads. They come from the impact of the polymer, okay? So that's the first series of tests we're going to be running is dropping these, and you have impact directly on those plastic polymer. You create half-sign types of impact. Now, the second series of tests, what it requires those trapezoidal impacts. So to create that, it said that we use pneumatic cylinders. So these guys can be pressurized at different pressure, obviously. And what it does, it's always, the first few times you do that, it kind of freaks you out a little bit when you pressurize it, because those two pistons go back up, poop, okay? And they make that funny sound, okay? And so when you drop the table, after that, the impact occurs when the plunger hits the piston, okay? Not when the programmer hits the felt pad. So you create different types of impacts. So, yes.
And how does that, I don't understand how the product experiences like that one versus the bottom one.
So this versus this?
Yeah.
So on the table itself, there's an accelerometer that is bolted on the table, okay? Mm-hmm. And it measures acceleration. So if you drop the test and you create an impact on those plastic programmer, okay, the acceleration when the table hits, okay, will look something like this. If your product is attached to the table, that's what it feels, okay? Because it's a rigid table, as it's mentioned before. So all the impact felt by the table is directly transmitted to the product.
Oh, okay, got it.
Okay? Does that make sense?
Yes.
Okay. So here, there's nothing, obviously, on the table, but you will have a product on top here. So this is what a damage boundary curve looks like. It's pretty straightforward. It cannot be simpler than that, okay? So what you have on the x-axis, you have a velocity change. And on the y-axis, you have acceleration. And the test we perform is to create actually this horizontal line and this vertical line. And when you connect them together, you have a rounded edge here. This creates what's called the damage zone. Okay, so this is where if you have a combination of certain velocity change and certain acceleration, if that combination is a point in that zone, your product is going to get damaged. Okay, so what does that do physically? Okay, and why do we have damage and no damage? Here's is the best way to illustrate these things. So the first point, number one, you see is right here, okay? So maybe I should mention that first. If you take that horizontal line, okay, and you extend it here, that intercept on the y-axis gives you the critical acceleration. vertically, if you extend that to the x-axis, that gives you the critical velocity change. So point 1 is here, okay? What you have is you have an acceleration that reaches a level that is higher than the critical acceleration, but has a lower velocity change than the critical velocity change. So let me turn back on the lights. So impact pulse, okay, for point 1 would look something like this, okay? So what you have is you can have a very large acceleration, very large maximum acceleration, okay? But a small velocity change. And remember, I told you before that the velocity change corresponds to the area under the curve, okay? So that means that this impact happens over a very small period of time. So you have a very narrow type of profile. So in this case, okay, you have no impact or no damage because time, if you want, is too short, okay? The shock can't be absorbed by the product. In a way that has to do with the frequency. It's such a high frequency that it's not very well transmitted to the product. And also, because there's very little area under this, even though there's high acceleration, there's very little energy in that impact, okay? Because the area under the curve, which corresponds to velocity change, also corresponds to the energy level of that shock. Does it make sense? So, area under the curve is a velocity change, and that corresponds to the energy of that impact. Point 2, okay, is right here at the bottom. So you have a very large velocity change, but you have a very limited acceleration. So you have a pretty flat profile like this. So in here, there's plenty of energy. You can have a very large area, but the acceleration is just too low for the product to be damaged. So something like this is, in a way, what you want to accomplish using cushioning, right? You want the velocity change to happen over a long period of time and reach a lower acceleration level, okay? So you have a lot of deformation, okay? So that's what I don't want to confuse you here, okay, by the fact that I talked about cushion, okay? All of these tests are applied on a product, a bare product, okay? That's very important. And 3, you have obviously the shock carries both enough energy and have also an acceleration level that is higher than the critical acceleration to create damage. So this is what happens in those different zones. So how do we construct a damage boundary curve? Okay, using this. So there's different steps. Step 1 is to determine the critical velocity change. So I'm going to jump from slide to slide quickly, okay, just to show you. So you have a graphic here that illustrates almost everything. Okay, that's the last slide, I think. So the step 1 is to work on that vertical line here that illustrates or find the critical velocity change. So to do that, as you will see, we'll use half-sine type of impact, okay, to do this. So we have to use multiple impacts. So step 1, okay, what you have to do is to attach your product rigidly on the shock machine. That's pretty straightforward. Now you need to expose the product to a series of half-sine shock pulses of short duration, 2 to 3 milliseconds. To do that, that's why you use the polymer programmers, okay, those black cylinders that were on the picture earlier. But you need to have this with different acceleration levels. So how do you affect the acceleration level for these tests? You increase the drop height until damage is observed. So in a way, the duration of the impact is controlled by the programmer themselves. So this is really short time. And what you do is you drop from a low height and you progressively increase that until you get damage. So initially you start the process with a low drop height, like 2 to 4 inches, okay, and use a drop height increment of 1 to 3 inches typically. ASTM use a change in velocity an increase in velocity change by 0.13 meter per second. It's just harder to control the velocity change, particularly with our machine. We lost this capacity, so we can basically play with the dropout. So depending of your product, depending how many product you have available, okay, that's what you will have to do. So typically as well, if you think about this, so let me ask you this. Let's say you were to do a test like this. How many, would you use a new product from each drop, or would you use the same product for many drops?
New?
Who votes for new? So that would be, some people are like this, but in an ideal world, that would be the case, right? Because the thing is, if you have multiple drops on your product, you may get fatigues, right? Okay, you may have some parts that at some point are going to get damaged, not because of the last impact, but maybe the accumulation of many impacts. So in a perfect world, you should use a new product every time, okay? Sometimes people use the same product, okay? And then when they get damaged, then they can use another product and start from that starting point and see if they get the damage with the same drop, or if they can get one or two more drops before damage occurs. Things like this. There's not, again, a perfect or a solid hard line that you have to follow absolutely, okay? Because people are limited sometimes. Obviously, if you have like a very simple product, you may not have to do that, but if you want to find the fragility of a product, sometimes, for example, that gas chromatograph, you may have to drop it, okay? So that will cost a lot of money if you have to do like 20 drops, okay? And not just 20 drops, but 20 units are get damaged. Because typically as well, I think we're going to talk about later, this should be done for different orientation, okay? So that's a lot of product to damage. So how do we identify the critical velocity change? This would be the velocity change corresponding to the point between the previous point and the point where damage was observed. A conservative approach is to establish the critical velocity change at the point just before damage was observed. So it depends what you want to do. There's people using different technique. Sorry, I'm going to go back to that last slide here. So what you have here, by increasing the drop height from test to test, you increase the velocity change, okay, because you have a higher drop height, so that means you have the impact velocity is going to increase, okay, and you increase this acceleration as well because you're having a larger velocity change over a constant time. So you go this way, okay, then you don't have damage. Here you have damage. So the conservative approach is to fix this as being the limit, okay? Some other people, ASTM suggests that it's going to be somewhere between those two to use an average value. So it depends, yes.
Did you say that the damage occurs on the boundary or once you're
That's the damage.
So even when you're on the boundary line, damage isn't occurring yet?
So that's the way that some procedures dictate you to do it. So that's the conservative approach because you have like little increases in drop height. Remember, 1 to 3 inches.
Yeah.
So the conservative approach is to fix that critical velocity change there. But some people will fix it a little bit higher. Okay, and at some point, let's say you use the one product to do all of this, then you have damage there. What you may want to do is take a new product, start here, okay, and see what happens, okay, to adjust it. So that will be the first step, okay. Critical velocity change, you use half-sine impulse, and you drop them from an increasing drop height until you get damage. So step 2 is to determine the critical acceleration level. So that is the horizontal line, okay. This is what is typically referred to as the product fragility. So to do that, we need to create trapezoidal impact. Yes.
You said that the area under the curve is the energy of the impact, right?
It corresponds to the energy of the impact.
So how do you know, like for this case, that if you make this like taller, how do you like you can adjust this so the area is the same. So how do you know like this doesn't dip up here in the damage zone? Does that make sense? Because if it's like if it's related exactly related to the area under the curve, you can always increase this and make it higher until the areas are the same. So maybe how do you know it doesn't dip here like this?
Well, I don't. Why would it do that?
Like because you keep going up, you're gonna increase this, and then eventually the areas are gonna be the same. Does that make sense? No? You keep increasing the acceleration.
No, but you increase the velocity change as well.
Well, no, like you keep the velocity change fixed.
But you can't.
No, you can't.
No.
Oh, okay.
Because you increase the drop height, so your velocity change is going to increase.
Oh, okay.
Okay? Does it make sense?
Yeah.
Okay. So the question was, on that impact that one was thinking that we can just increase basically the drop height with keeping the same area, but you can't, okay? Because every time if you drop, you adjust the drop by increasing the drop height, you increase the velocity change every time because the impact velocity is going to increase. This is going to be different, okay? So this is going to be similar to what you're talking about. So in this one, we create trapezoidal shark pulse, okay? You want to do these because these carry more energy. That's the maximum energy you can carry basically for a certain acceleration level. Because think about this. This is what is closest to basically a square waveform. So that means that has more energy for a certain maximum acceleration than any other profile like this. If I reach the same maximum acceleration, because this has a lot less area than this. So the square waveform or the trapezoidal impact carry more energy than for a given maximum acceleration than the half cycle. So how do we do that? Is we gonna adjust the pressure, okay, in the pneumatic cylinder. Okay, so as you increase the pressure, basically they become stiffer. Okay, it's like having a stiffer and stiffer cushion, right? So to start with, we have to select a constant drop height. Okay, and that doesn't change throughout the series of tests. We pick a drop height that is higher than the critical. That creates a velocity change that is higher than the critical velocity change, okay? And to do that, we need to pick a drop height that will give us a velocity change past this point. So a lot of, including ASTM, they tell you to use a value of pi over 2 times the critical velocity change, okay? But to make sure that you're past this, typically what you do is twice the critical velocity change, okay? So if you select a drop height that will be twice the critical velocity change, you know that you're going to be past that curved, okay? And you're going to be clearly on that flat portion of the damage boundary curve right here. So let's see if I can go back there. So that's what it mentioned here. Some packaging engineers, as well as ASTM, recommend to double the critical velocity change to ensure that the test result on the horizontal portion of the damage boundary curve. So then what you do is you attach an undamaged product to the shock machine and expose it to a series of drops. In this case, the drop height, again, is constant, okay? But between each shock, you increase, okay, the pressure in the pneumatic cylinders. So what happened in this case is you have the same velocity change, okay? But you change the time at which that velocity change occurs, okay? So what you end up with is something like this. So if the area under the curve is the same, okay, it's just now going to get higher and higher and higher because if the cushion is stiffer or if there's more pressure in the cylinder, instead of compressing and having that velocity change happen over a long period of time, it's going to happen to a shorter and shorter time, okay? So you have larger and larger acceleration as you go up And again, the same thing applies. This is a conservative approach, but you can put the critical acceleration change midway between those two, okay? Where the point when you have damage and the point previous where you didn't have damage. So, let's see. That's what is described here. So, next steps is to connect the horizontal to the vertical line. Okay, you have to use a curved line. This is a little bit arbitrary to create that. And then you have to, process must be repeated for each product orientation susceptible to occur during distribution and transport and distribution operations. So, most likely you're going to have one damaged boundary curve per each orientation. So that's where it gets pretty tedious, right? But if you have a product with many components and it's expensive, it may be worth it knowing what is that level at which you have damage or not, okay? Because in the long run, that may save you a lot of money if you want to avoid over-packaging your product. So, this is also important here, is that the mode of damage may be different when performing step 1 and step 2. So a damage due to a half-sign impulse by increasing the drop height can be one part that it snap off, okay, or breaks, okay, and the damage when you have step 2 might be a different part. I think the classic example that they give is, for example, let's say this is a simple product, but let's say you have a stem glass for wine, for example, okay? So you may have one of these tests where the stem breaks and the other one, actually, the glass itself breaks, okay? It depends of these two different cases. So, let me see. Okay, so that is damage boundary curve, and obviously this is one of the biggest use for shock machine is to be able to reproduce that and to identify the fragility of the product. Next thing we're going to do you guys have any question on this? Does it make sense? Okay. Next thing we're going to do is start discussing about actually cushioning. Okay. So we learned about shocks. Okay. And we define some equation to be able to look at maximum acceleration, deformation, and look at a little bit of energy associated with impact. We then discuss product fragility. The next step, if you think about it, is now we need to be able to select a cushion, okay, that'll be able to protect our product, okay? So how do we do this, okay? There's different ways, okay? Obviously, there's a lot of people that still use just trial and error, or they try something and they drop it in the lab and it works, and they ship it and they don't worry about it, okay? But again, it depends on what product you need to protect and your meaning how much budget you have to develop packaging. It depends on how many products you'll have to ship, because all of these, if you want to optimize the packaging system, if you have thousands and thousands of products to ship, that may be worth it. Okay? So again, this is kind of the ideal procedures you should do, okay? But it's not always what's going to happen in real life. So, cushioning material, we've been talking about them for a long time, and we know that they are used to protect against shocks and impacts. We know they cause issues with vibration. That's how we introduce themselves. Okay, we know that together the product and the cushion system have a natural frequency of their own, depending on the stiffness of the product, stiffness of the cushion, and the mass of your product. But the idea, they may cause problem because of vibration, but they're there to protect against shocks, okay, vibration. So upon impact, a good cushion would deflect and absorb a lot of the mechanical energy associated with the impact instead of transmitting it to the product itself. That's the goal, okay? And that's when we discuss in detail with those acceleration these equations for maximum deflection and acceleration. We went through that physics, and we talked about this. If the cushion is too stiff, okay, is a cushion that is too stiff will transmit too much energy to the product, and the same situation can happen if the cushion is too soft, okay, because in this case, it's going to deform so much that it's going to exceed its working length, and you're going to have the product that will bottom out, okay, right here. So that is an issue as well. So the deflection associated with the cushion is referenced typically as the working length. Okay, the working length vary with the physical characteristic of the cushion and can range between 25-75% of its initial thickness. Okay, it varies, but obviously you cannot compress it all the way down to 100%. So what kind of cushioning material exists and you've seen? Okay, so you, without designing any of this, you do have experience on these because as consumer, we buy product and we see how they are packaged. Actually, some of you may have started to pay more attention about this before you start taking any of these classes, hopefully. But one thing we've seen is, one type is loose fill or dunnage. Okay, so the classic polystyrene peanuts, okay, shredded or crumpled paper, we've seen that all the time. Okay, most of the time these are inexpensive, but also inconsistent in performance. Okay, I should bring some stuff to show you. Maybe I'll show you in the lab on Friday. So what happened with these is obviously we all experience that the peanuts things shift, right? Unless depending on how it's packed, but things are allowed to shift during transport, so at some point you can have something that was like surrounded by peanuts and end up on the wall of a box or in the corner, and then you can be exposed to damage or to impact, and potentially damage. Paper as well can be used, can be shifted, and can be compressed at some point. Paper material, when they're exposed to many impacts, okay, or vibration, they change form, right? So they're going to compress, and they may not do as good as a job. As engineers, what is the other, I would say, problem with these?
Peanuts?
I'm sorry?
I was saying peanuts. That eventually, like, it can, like, the peanuts can just move out of the way, and
Yeah.
the product can end up
Yeah.
at, like, a corner or something.
Okay. So, what else I would say you don't like about these things?
Are they eco-friendly?
Paper is, like, I would say, eco-friendly. Styrofoam peanuts, no. But you've seen other types of peanuts, right? There's starch peanuts that you just put in water and they just melt. But does it look good? It's messy, right? And usually it's not very efficient. Obviously, if you are an Amazon type of company and you have to rebox product, okay, there's not a lot of option for this, okay? What is another option that is not presented for dunnage? Yes.
The air pack.
Air packs, okay, air pillows, okay. You see that quite a lot. You also sometimes see for some product actually Instafoam packed. Have you seen these? That they are basically polyurethane. Basically, you puncture them, okay, and they're going to inflate, and you can put your product in there, and it's going to try to fill up the void. These are actually pretty good, okay, because they will mold to the box in your product, but they are very expensive, okay, like $10 each, okay, very expensive. So if you ship hundreds of product, that is not a good way to go. Air pockets, okay, or bubble wrap or something like this is going to be a better option. But all of these plastic, unless you recycle them, it's not very eco-friendly like it's mentioned. So die cut or folded corrugated paperboard insert. So that you see that a lot. I'm going to see some pictures later on, but this is inexpensive, can be recycled, and corrugated is actually a pretty good shock absorber, right? And is depending on its configuration. But as all paper product, humidity is not his friend, okay, and multiple impacts can create permanent deformation and then cause problem. Molded form, we've seen that as well, so that can be a paper-based pulp, okay. You think about trays, for example, for your coffee or things like this, so you can mold pulp into different types of shape to absorb, to basically match what you're dealing with your product. You can have open cell foam as well, that can be urethane, okay? You can have closed cell foam, that can be polyethylene or expanded polystyrene. These are all things we see quite a lot. So for corrugated, what you can see is you have different ways to do these, okay? So one product that is used quite a lot is honeycomb, okay? This is really stiff boards, okay? So if you have a heavy product, if you want to maintain that in place, you can basically have shape that will match your product, and you can have different level of them. So they are pretty good, and they are, partially if you have a heavy product, okay? If your product is light, it may not be able to deform in the direction of the honeycomb, but if you're shipping like mechanical parts, like engines or something like this, motors, even in the axial direction of the honeycomb, then you can have pretty good protection. If you have it in the other orientation, then you're going to have also a little bit more protection, like softer cushioning. Let's say the impact was done in that direction. Now with corrugated, it can be created into different types of cushion. And again, depending on the orientation, you're going to create quite different stiffnesses. So if you have the flute going up vertically and you put something there, that's going to be really rigid, okay, really stiff. If you have it, the flute flat like this, then you're going to have something softer, and you're going to have something a little bit different as well, depending on these orientation. And again, you can have different thicknesses, different types of them, okay? You can have them cut into different sizes, but these are ways to use corrugate as cushioning material. A relatively new material, I don't know if any of you have seen that, okay, is mushroom packaging. Have you guys seen that before? So this is pretty cool stuff. It's been around now for probably, makes me feel old, but maybe 10 years or something like this. But what they do is they use a very similar approach than for polystyrene. They have molds, okay? But instead of injecting polystyrene in those molds, what they do is that they fill the molds with a biological material, okay? A substrate on which they then, after that they inoculate with a mushroom, okay? So what happened then is they keep it in the right condition, and the mushroom grows and fill up the mold, okay? And depending of the substrate that is used, so what kind of substrate can be used? You can have like cotton husk, rice husk, hazelnut shells, a bunch of different things, okay? They can be treated, okay? Then they inoculate it, then put it in the mold, and then they grow. It takes about 5 days for them to grow. And then the mold is basically heat treated, the mold, but the mycelium itself is heat treated to make it inert, okay? And you create that cushioning material, okay, that can be molded into different sizes and can create, they supposedly can create different as well, stiffness, different properties depending on the process they're using, probably the density of the substrate they're using for inoculation, and other things that I'm not sure about. So again, it can be tailored. So once the consumer gets this, you can compose that 100%. It can be degraded. And you already have a bunch of companies. There's more and more companies now, if you go on their website, that are using them for their product. Dell was one of the first one that used their product for their packaging their system. So I'm going to don't pack everything. What I'm going to ask you, we have 5 minutes, right? So take out a little piece of paper, okay? We have a lot of people that did not show up or arrived late, okay? And I want to do a little quiz, okay? So close up your slides and things. It doesn't matter if it's a small piece, if it's half a sheet of paper on a share. Seems like most everybody's ready. So I want you to just write your name first, okay? That's not the quiz though. But I want you to draw me, okay, I would say classic shape of a damaged boundary curve. And on that damaged boundary curve, I want you to identify the axis, okay? And also the critical velocity change and the critical acceleration. So the classic shape of a damaged boundary curve, identify what properties on each axis, and identify what is the critical acceleration and critical velocity change on that schematic. Thank you. And once you're done, you're free to go.